So the analysis of Trie parameters is one of the most challenging in the analysis of algorithms and quite interesting to contemplate. So that's what we're going to look at next. So again, it's the basis of understanding performance in lots of large-scale important applications that are part of our infrastructure right now. So one of the big questions is, how much space does a Trie take? Well, it's the total number of external nodes. And then if you have the number of strings you're representing, then you can figure out the number of extra nodes. That's the number of void nodes is really the extra space that you're using. What about the expected search cost? Well, like with BSTs, that's the external path length. That's the distance from the root to all the external nodes, the average distance. So external path length, average external path length of this Trie is 3.92. That's the search cost. Now you notice that even if half your nodes are void, that's only going to add half to this extra cost. So that's part of the reason that Tries are effective. You can have plenty of void nodes, and it's not going to affect the search cost all that much. And then leader election, that's the length of the rightmost path, as I talked about before. It turns out we can analyze all of these. I'm going to talk about external path length, and the others will be exercises. And again, the easiest model, the usual model, is to think of the Trie as built from inserting n infinite random bit strings. Eventually they're going to differ, and that's where they differ, that's where you're going to get a non-void node that might represent an infinite tail, but we don't care. The bit strings distinguish themselves. Eventually the Trie represents them according to distinguishing them on the leading bits. And from an analysis standpoint, it's makes for a reasonable model because we can assume at every node that we randomly go to the left or to the right. And this model fits real data perfectly well when it's been studied. So the starting point, if you think back to the analysis that we did for binary search trees, is very similar. It's just that, so that is, we have a Trie of size n. There's k on the left and n minus k on the right for some value of k. The difference is that, two differences. One is what's the probability that there's k nodes on the left, which in the case of binary search trees was just 1 over n. And the other difference is that you might have no nodes on the left and n nodes on the right. So that's a technical thing that definitely comes directly from the definition of Tries, but it makes the recurrence just a tiny bit trickier. So that's the recurrence down at the bottom. What's the probability that when you have n strings, n random strings, what's the probability that k of them start with a 0 bit? It's just 1 over 2 to the n times n choose k. Then the external path length of a Trie is, as you look at the root, that adds n to the external path length because there's n nodes down below it. And then 1 over 2 to the n, so it's a probability that there's k on the left, which is n choose k over 2 to the n. And then it's the external path length c sub k, external path length n minus k with the appropriate starting conditions. Again, it's just a little tricky to realize that there's a Cn on the right-hand side when k equals 0. So for BST, the probability that there were k on the left is 1 over n. We looked at random Catalan trees where that's the probability is k on the left is a Catalan number, and we had the Catalan distribution. And for Tries, it's a binomial distribution. So that's the recurrence, and we can use that to calculate small values or the distribution, but that's the one that we want to solve. And again, just by correspondence to the distributions that we looked at for random Catalan trees and for binary search trees. For binary search trees, the distribution is totally flat, equally likely for any node to be at the root. For Catalan trees, remember we found that they were very likely to have one side or the other have only a small number of nodes. And so the distribution was very skewed and very skinny trees. For AVL trees, we're trying to make them more balanced, and the distribution shows this amazing pattern that we haven't characterized analytically. And for tries, the probability that a roots K is binomial, and that's really a characteristic that we're looking for that's going to tell us that these things are going to be pretty well balanced, because that tends to n over 2 is the most likely thing, and within square root of n over 2 is where the divisions are mostly going to be, which means that it's going to be pretty well balanced. But let's look at that analytically. Now, I'm not going to cover every detail in great detail, but I think you'll see how we go from one step to the other, and you can check details offline. So this is the basic recurrence. We're going to use the exponential generating function for this. And the reason is the n choose k allows us to, if you divide by this equation by n factorial, then you have c of n over n factorial on the left. And then sum that on all n, you get c of z using the exponential generating function. And then the n choose k part of it is it's a convolution of ck over k factorial and 1 over k factorial. And without very much calculation at all, you can verify this formula. C of z equals, this is by dividing by n factorial, multiplying by z to the n, and summing both sides. Pretty quickly comes down to this formula. And you can also actually get this directly through the symbolic method with an appropriate operation having to do with the way trees divide. So very simple formula on the generating function. It's a convolution of e to the z over 2 and c of z over 2. That's the generating function equation. Now, it's not can't be characterized as the simplest of generating function equations that we're going to be able to solve explicitly because we have that z over 2 in the argument. But one way to deal with it is to just iterate. So if we apply the same equation for c of z over 2, just plug in the same equation, then the z e to the z becomes z over 2 e to the z over 2, minus z becomes minus z over 2, and then 2z over 4 c to the z over 4. We can iterate, and then the argument gets smaller and smaller. And simplify, so that's just collecting terms, but we still have an equation that we can iterate. And in another step, you can see the pattern is that what we're going to wind up with is z times e to the z in every case, and then we have the declining z over 2, z3, 3z over 4, 7z over 8, and so forth. So we get a sum of terms of the form z times e to the z minus e to the half z, 3/4 z, 7/8 z, and so forth. So it's not, you have to prove that this thing really goes away as you go to infinity, but anyway, that's the iteration that we get. An explicit formula for the generating function for the average external path, that gives us the average external path length in a trie. Okay, so we're looking for coefficient of z to the n in that. Well, n factorial times z to the n in that. And if you go ahead and expand the e to the z multiplied by n factorial and get the coefficient of z to the n, then we have this difference 1 minus 1 over 2 to the j to the n minus 1 sum on j. Again, that's a fairly simple formula, explicit formula for the average external path length in a trie. It still does have the infinite sum, and we're going to have to work with it a little bit. I'm working through this with elementary analysis just to make sure that people see what underlies this solution, and because we get to a kind of surprising result, and it's good to see what's underlying what the structure is, and so that's what we're going to do. To characterize this fully analytically requires complex analytic methods that we'll talk about in part 2 of the course. What we're going to see is on the next slide, we're going to use if you use an x-log approximation, this thing becomes like 1 over 1 minus e to the minus n over 2j. That's not a difficult calculation using x-log. And the next slide will show that that's pretty close to n log base 2 of n. So that's the external path length in a trie. This step is not difficult. I didn't mean to skip through it so quickly, but it's not difficult at all to show that with x-log. But now what I'm interested in is looking at this sum on j greater than or equal to 0, 1 minus e to the minus n over 2 to the j, how we're going to characterize that. And that's a really interesting function to take a look at it. What I'm going to try to do with this analysis is try to isolate the periodic terms. There's an oscillation in here, and I want to try to isolate the part that oscillates. And so the way that's going to happen is we're going to take the function log base 2 of n, and we're going to work with the integer part of log base 2 of n. And then the fluctuation is every time you come to an integer, as you go from one integer to the next, there's fluctuation in the function as you're working with the real function log x, but you're only picking off the integer parts of it. And let's see how it works. So all we're going to do is take that infinite sum, and we're going to break it into 2 parts. The part where j is less than floor of log n, and the part where it's greater than or equal to floor of log n. So that's just split the sum into 2 parts at that one point. And the key thing to notice about this is when j gets bigger than log base 2 of n, then 2 to the j is going to be bigger than n. And so we're going to have minus n over something huge. We're going to get a number very close to 1. It's going to go away. And when j is small, like say j is 2 or something, we have e to the minus n, which is tiny. The sum is just 1. So basically, we're going to have log n terms that are very close to 1, and all the rest of them are going to be very close to 0, with just a little bit left in the center. So let's look at how that goes. In this case, we just split off the log n, so we get floor of log n. And then we have the second one, e to the minus n over 2 to the j, and that's just splitting the first sum into 2 parts. And then this one is the same, so no change there. So now what we're going to do is let this j go as far negative as it wants. It doesn't matter, because if that j goes far negative, this thing is exponentially small, so it doesn't matter. And we're off by an exponentially small amount. So, and that's going to allow us to combine the 2 sums in that part. So this is change j to j plus log n in this sum, and same way as change j to j minus log n in that sum. And so now we have some floor to the log n's coming into these sums. But then there's n over floor to the log n. Well, that's like taking the function log n, subtracting off the integer part. All that's left is the fractional part. So the end sum of this thing is, what's floor of log n? That's the biggest integer less than log n. That's the function log n minus floor of log n. As n increases, this function fractional part of log n goes from 0 to 1 and back again. So it's a fractional part of log n. It's an oscillating function. But these other functions also are just functions of the fractional part of log n. And again, I skipped through just a tiny bit of subtracting log n from floor log n, but you'll see that works out. So now I have these three parts that are all functions of the fractional part of log n. That is, they oscillate. And so this is my external path length over n. So right here, this is a proof that it's asymptotic to n log base 2n, because the other things are all 0 to 1. But what's really interesting about this is we look at these functions. So this is the proof that I just went through. If you have that recurrence, then that leads to this result. But let's look at it in just a little more detail, these three terms. The first one is, again, the fractional part of log n. And so that's just a plot of the fractional part of log n. Now the second one is this sum of e to the minus 2 fractional part of log n minus j. And that one also oscillates as n increases, it oscillates, and that's the approximate magnitude of it. And then this is this third one that also oscillates. So we have these three terms that oscillate that we're adding together to give us the difference between log n and our function. And what's amazing is if you add these all together, you get a smooth oscillating curve that's very tiny in magnitude, 10 to the minus 6 in magnitude. Not something you would notice if you didn't do the math. And we're going to see in part 2, we'll look into a little bit how to do the math. But certainly it's quite a surprise to see these functions that are so different in character adding up to this continuous function. This is a proof that Cn of n minus log n is this strange oscillating function that you wouldn't see unless you look out to 6 decimal places. And the question is there a reason why a recurrence like that, which seems such a natural recurrence involving our integer costs, should have this strange periodic behavior? And the answer is yes. We're going to see when we get to complex analytic techniques in the Mellon transform that there's a perfectly valid explanation for such periodicity. And not only that, it's bound to appear in the analysis of lots of algorithms that are based on properties of bit strings, like tries. So applying that result and taking a look at the distribution that we get with tries, you can see that it's even more tightly bound towards a particular shape, basically divided at the center, even than BSTs. And so just to quote the results that we get from this kind of analysis, the extra space is about 44% of the external nodes are void. The expected search cost is about n log base 2 of n. So that's a number of bits you have to examine. And that's a very acceptable search cost and competitive. And for leader election, well, that'll be an exercise. That's a discussion of Trie parameters.